Welcome back, engineers. So, have you ever looked at a microscopic semiconductor integrated circuit, or maybe a massive high-voltage power capacitor, and asked yourself, how exactly do these devices store such massive amounts of electrical energy without just shorting out completely? Well, it's a fundamental mystery of electrical engineering, and today, we're going to solve it. We're going to master one of the most absolutely critical concepts in electromagnetisms, the dielectric constant and dielectric strength.
Now, you might be wondering why mastering dielectrics actually matters for real-world engineering. You really just have to look at the massive push to shrink modern electronic circuits. As our source texts from Sadiku and Haidt point out, high dielectric constant materials are exactly what allows us to push the state-of-the-art in semiconductor ICs. See, the higher the dielectric constant, the more charge you can store, and the smaller you can make your entire circuit. By the end of this explainer, you're going to walk away with a rock-solid, practical intuition of exactly how this works, right down to the math.
Okay, let's dive into this. Here's our roadmap for today. First, the real-world dielectric hook. 2, polarization and the atomic zoom-in. 3, the math of dielectrics. 4, a step-by-step example problem. 5, the breakdown gotcha. And finally, 6, our summary and key takeaways.
All right, part 1, polarization, the atomic zoom-in.
To really understand how dielectrics manage electric fields, we've got to look past the macro surface and dive straight down to the atomic core. The core difference between your standard conductor and a dielectric insulator is that in a dielectric, the charges are bound. I want you to use this never-forget analogy. Think of the atoms in a dielectric material kind of like a crowd of people tied together by incredibly stiff rubber bands. The positive nucleus and the negative electron cloud are bound together by finite forces. When you apply an external electric field, which we call E, it acts like a force pulling on those rubber bands. The positive charge is displaced slightly in the direction of the field, and the negative charge gets displaced in the opposite direction. The rubber bands stretch, right? But they don't break free. This stretching creates an electric dipole, and when this happens, we say the dielectric is polarized.
Let's put a formal definition to what we just visualized. Polarization, represented by the capital letter P, is defined as the total dipole moment per unit volume of the dielectric. It's measured in coulombs per square meter. So macroscopically, polarization is simply the bulk measure of all those tiny atomic rubber bands stretching and aligning across a given volume of our material.
Moving right along to part 2, the math of dielectrics.
Of course, understanding the rubber bands is great, but as engineers, we need to actually quantify it. Let's transition into the mathematics and break down exactly how these atomic shifts affect the electric flux density in our systems. Here's our first foundational equation, D equals epsilon naught times E plus P. Let's explicitly map out every single variable here. D is the electric flux density, epsilon naught is the permittivity of free space, E is the applied electric field, and P is that polarization vector we just talked about. What this equation is physically telling us is that the net effect of a dielectric material on the electric field is to literally increase the flux density D inside it by exactly the amount of polarization P. The material is actively adding to the field's flux density compared to just a pure vacuum.
But how much polarization do we actually get for a given electric field? Well, for linear dielectrics, P is directly proportional to the applied field E. Look at this equation here. P equals chi sub E times epsilon naught times E. That new variable, chi sub E, is called the electric susceptibility of the material. Physically, chi sub E is a dimensionless measure of how sensitive, or how susceptible, a specific dielectric material is to an electric field. Simply put, the stretchier the atomic rubber bands, the higher the susceptibility.
Now watch what happens when we substitute our P equation back into our original D equation. D equals epsilon naught times the quantity 1 plus chi sub E all times E. The term inside those parentheses, 1 plus chi sub E, that is our star player right there. We define that as epsilon R, the relative permittivity, or the dielectric constant, and this allows us to dramatically simplify the whole thing down to just D equals epsilon times E. Epsilon, without the naught or the R subscript, is the absolute permittivity of the dielectric. It beautifully wraps up the free space constant and the material's specific stretching ability into one highly practical variable.
And this brilliantly illustrates our next section, part 3, step-by-step example problem.
This elegantly simplified formula is exactly why engineers love the dielectric constant. It makes the math remarkably clean. Let's move to a practical, step-by-step example problem to see how this actually works out in reality. Let's set up example 5.10 straight out of Sadiku's text. We're looking at a dielectric material where we're given an electric flux density, D, of -2 AY nanocoulombs per square meter. We're also told this material has a dielectric constant epsilon r of exactly 2. Our job is to calculate the electric field E. To do this, we just rearrange our simplified formula, E equals d divided by the product of epsilon naught and epsilon r.
Let's methodically plug in our numbers here. In the numerator, we have our d, -2 times 10 to the -9th in the AY direction. Now, look really closely at the denominator. We plug in our dielectric constant of 2, but for the permittivity of free space, epsilon naught, we're going to use the precise fractional equivalent from the text, 10 to the -9th divided by 36 pi. This is a massive pro tip for textbook problems. Using 8.854 times 10 to the -12th here, we'll just create a really messy decimal. Using 10 to the -9th over 36 pi makes the next simplification step incredibly clean.
Notice how the math just cleans up perfectly here. The 10 to the -9th in the numerator cancels right out with the 10 to the -9th in the denominator. The 2 cancels the 2, the 36 pi flips right up to the numerator, leaving us with exactly -36 pi AY. Multiply that out, and we get our final electric field, -113.1 AY volts per meter. It's a perfectly clean derivation that shows exactly how the material's dielectric constant scales the field.
All right, that brings us to part 4, the breakdown gotcha.
But wait, there's a catch. In engineering, math only models reality up to a certain point. What happens when those equations, or more accurately, the materials themselves, break down? The theory we just walked through assumes an ideal dielectric. In an ideal state, those atomic rubber bands stretch under finite forces, and that allows the capacitor to store massive amounts of energy. But practically speaking, no dielectric is truly ideal. If you apply a sufficiently large electric field across a material, the pulling force simply becomes too great. The rubber bands snap. Electrons are literally pulled completely out of their molecular orbits. The material abruptly stops acting like an insulator and instantaneously becomes a conductor. This catastrophic event is what we call dielectric breakdown.
And that brings us to a parameter that is just as important as the dielectric constant, dielectric strength. By definition, dielectric strength is the maximum electric field that a given material can tolerate or withstand without electrical breakdown occurring. It is a hard physical limit. If your electric field E exceeds this value, your D equals epsilon E equations immediately go out the window because your dielectric is now essentially just a wire. This is the exact reason a poorly designed high-voltage capacitor will literally explode on the bench.
So the crucial point is, well, let's wrap it all up in part 5, summary and key takeaways. Understanding dielectrics requires mastering both their ability to polarize and their physical limits. Let's lock in our long-term retention with a rapid-fire 3-point recap. Number 1, dielectrics polarize under electric fields. Never forget the rubber band analogy. Bound charges stretch, forming dipoles, but they absolutely do not flow. Number 2, the fundamental math. The formula D equals epsilon naught times epsilon r times E perfectly links electric flux density, relative permeability, and the electric field into one beautifully cohesive expression. And number 3, the gotcha. Exceeding a material's dielectric strength strips electrons right from their molecules, causing catastrophic conductive breakdown.
Which leaves us with a critical question for your workbench. How will you account for dielectric strength and not just the dielectric constant in your next high-voltage circuit design? Because making things smaller is great, but keeping them from shorting out, well, that's what makes you an expert engineer. If this explainer helps clarify the physics and the math for you today, hit subscribe for more EMC and automotive communication protocol survival guides. Keep designing, and I'll see you in the next one.